要 technical issue and need to solve. 想要 HDMI 接到的这个，那个是我自己带来的。
对，我在找这边是。又掉下去。
哦，所以它是掉的。
就是谁要上课？就是我们上次有一个，就是来这边然后自助中途，然后把我们的系统都直接破了。好。遥控器。需要把它调到20，设计都没问题。
那边有 OK 吗？
应该可以啊。
现在画面还没连到老师的电脑。
可是我已经接上了，我的电脑我已经接上了，跟这个无关啊，我的电脑我已经接上了。
你可以帮我看一下输出啊，因为现在这个系4这个第2个应该，然后老师我比较担心是你的那个接头。
上次来完全没问题的。
没有，因为原厂接头14号，有时候会有奇怪颜色的问题，因为这一台它有时候讯号会有问题。
那我要怎么弄？
帮我看一下。讯号有没有送到？应该会有2个这个一台。318应该是。
我应该选哪一个？
因为这样可以正常。
哦，
就是 A B 下开始。
我可以先把两个兑换一次。
兑换是不是？
对，两个 HDMI。
两个 HDMI 兑换。
哦。所以我不确定现在是哪一个。就是。有，现在这个是有的。
嗯。
对，那你们那边有吗？
这边 Do you see?
I don't see yours.
啊。
I don't have your signal.
It's problem with this.
所以，我猜可能跟这个有关。哦，是我去拿。我那边有，我再拿一个给你试试看啊。
好。对。It seems like there's some problem with this adapter.
Oh, okay.
Yeah,
because you need to charge yours while you're using it, right?
Yeah.
Can you try to? Is it the same kind of thing here? Does it work?
You see that? No.
Do you need to use this one?
Yeah, it's either this work or this one.
Okay.
So this is, but last week this is working. So
Yeah.
Okay. About now?
No. I don't have your signal.
It's still setting up. Alright.
你电可能要接，现在电。
那电源接在这个上面。
拔掉。如果是啊，换过了。好，这个。
这样子呢？
No, I don't have it.
But it's already back to original
Yeah,
one.
right. Okay.
老师，你再等我一下，我还有另外一个东西是，把一个需要1分，你就不用接两个。
OK，
你等我一下。
The same way. Okay. Wait, can you try to plug yours in this one?
有了。OK。Alright.
It seems like they're Okay, for the speaker, please put a file on my computer.可以的，拔来拔去之后，它就突然间可以的。你先留着好了。对，我先上课，因为我怕等下又弄半天。
好了，那 OK， 那就先上课。
好，谢谢。
first one.
This one.
Yeah.
Another one. Up here. Put your 5 here. You need time to prepare? Okay, maybe then we'll go start first. Go ahead.
Okay, hello everyone. My name is Arnaud Garbet, and I will run through the homework of the last week. So first, for the first question, which is generate 10,000 random number from Gaussian distribution with the mean with 20 and the variance of 10, and then we have to plot the distribution. So first, I start by defining the distribution with the function R norm. And then I calculate the mean and the variance of this distribution. And then we have to define the different coefficient to change the mean and the variance to 10 and 20. So for that, I based on this formula. And so I calculate the coefficients by this. So the variance of y is equal to variance with the coefficient a and the variance of x. So finally, we have here the variance we want, and this is the variance we calculate here, and with the coefficient a squared, and then we can obtain this one. And this is the line I write here. And for the mean, so we have a mean of y is equal to a mean of x plus b. So for a mean of 20, we already calculate the a before, so we can use it in this formula. And we can then calculate the coefficient b here. So then I define the new distribution with the mean 20 and the variance 10 with the different coefficient we calculated before. So it's this line, so I just multiplicate the previous distribution by a, and I have the b coefficients. And we can see the mean and the variance is equal to 20 and 10. And this is a plot of the distribution. Then for the second question, so it's generate 10,000 random number from a binomial distribution with p equal 0.5 and n equal 40, and then plot the distribution again. So first I define an empty matrix, and I create a loop to generate 10,000 uniform distribution. So I use the function runif with 40, which is the number of n, and a minimum and maximum of 0 and 1. And then, so I define a limit of p, which is 0.5, and all the value upper than p is true, and the value lower are false. So then I wanted to make a sum of the different true value, and I put all these totals in the matrix I created before. And then when I plot it, we can have this distribution. And then when we compare with the distribution we had before, we can see it's the same with the mean at 20 and variance around 10. So. And then for the last question, it's make a program that can select our candidates for presentation next week. So here I start by define a list of number, which is the number of students we have in a class. And then I decided to make a loop to choose two numbers until all the students are chosen. So for that, I create a loop for with 0 to the length of ID. And then these two first lines are made if the computer selects the same number 2 times, you have to restart. So if, oh no, sorry, it's not this part. This part is just to start by by two number. And then, sorry, so then if the two numbers chosen by the computer are the same, I want him to do it again. And then I print the two ID, so the two numbers selected, and I remove them from the list to create the set inside the same list. So after I will start again the loop with a lower number of ID inside until there is nothing in the loop. And this is what we can have at the end. Okay, thank you for your attention.
Okay, thank you. Any questions? Any question? No? Okay, maybe we'll go to the next one before we have a general discussion. Thank you. Give me the. This one, first one?
1.1.
1.1, yeah, that's right. Use this. This is mouse. Use this. I just need to push in the bottom. Up and down.
Hello?
Up. And wait. Then we'll start. Yeah.
So good morning. So this is my presentation for second week. And first, the question was generate 10,000 random numbers from Gaussian distribution with mean 20 and variance 10 and plot the distribution. I just use very simple code. I use R norm for getting the normal distribution, and I use n is equal to 10,000 mean, and as it was already mentioned in the question, that mean 20 and variance 10. So I use like this way, and where n is equal to the number of data set, like 10,000 random numbers. Mean is vector of means, like average of the numbers, and SD the deviation or variation. Then I just simply print the C and I got my result, and I plot with histogram. And the plot was here. The first one, this is my normal distribution histogram plot, where you can see that it starts with the minus value to the plus value. So this is the plot. For the second question, for the second.
How about binomial?
Yeah.
This one.
Yeah. Second question was the binomial distribution. As we all know that binomial distribution has two possibilities, like true or false or head or tail. So I choose here tossing a coin, where first I select one integer that has 10,000 array, or where then I choose the for loop where for the first there is no value, so that's why a is equal to 0. Then I toss my coin for 40 times. So there is 1 to 40, and for that coin, I chose that my result will be the head. So I give the logic that how many times, like S is like a counter. S will count how many toss will be there or how many head will be there. So for the first, it's like positive value or negative value, and I give a logic that if it will be head, then uh, if it will be head, then it will give the value will be greater than a. So I chose a normal distribution for only one value, and that give a number that is greater than 0. If that value is greater than 0, then I also give a logic like s equal to s plus 1. That means if it will give me a value that is greater than 0, then the number will add with the previous array. And then I put my all s inside the v integer, and then I print the v to get the binomial distribution number, and then I plot with histogram. Here the second one was my binomial histogram plot, where you can see it starts from the positive 5 to 35, and in the same question there was a comparison. So I use this code, but my system later will not work well, so I chose to show this separately. Here is you can see the comparison between the normal distribution and the binomial distribution. The difference is very clear. Here you can see that the deviation is more in case of normal distribution. But for the binomial case, the deviation is not so much. Like you can see that 5, 10, the deviation is very less. And another thing is, for the normal distribution, there is the number should be continue, and for binomial the number is discrete. So and the third difference is that normal distribution give me a negative value, but for the binomial case there is no negative or positive because that is a count. And for my third question, make a program that can select candidate for the presentation next week, and this program should select randomly, but avoid selecting the numbers that have been selecting before. For that, I choose one number. Like first, I select one student by using RUnif code that will select a student randomly. Like I choose UNIF code because there will be chance to select the choose student. Like the probability will be same to select any student. So I use this code RUnif where I will choose one. So that's why I put one, minimum one, and maximum. I decided that my class will have 18 students, and then I just print the C, and then I put that in another vector A, and then again, so first I choose a student, the student number will be fixed. So now I am deciding to choose another student. So that's why I run another like same code by with name with different vector. So the second student will be B. But I am not sure that B or A same or different. So that's why I use while loop, while A is equal to B, and if it is true, then generate another B. My logic is that. So this while means like until A equal to B, generate a new B. Okay, so it give me a new B. This previous B, I check like later I check with this B and that B. These two B are not same. So it's generate a new B. So this way I generate a new student. Okay, thank you.
Okay, so for the first question, we go back to the first question. Can you go back to the first question? Yeah, so I explicitly say I ask you not to use this. Okay, not to use this. I understand that there's a built-in function you can decide the mean and the standard deviation, but I ask you not to do this. Right. So the another one. So this is so basically this is what I expect you to figure out, because if you want to shift the mean, we just need to add how much we need to shift, right? And if we want to change the variance, we just need to figure out how to change that variance. Okay. In fact, if you want to change the variance from 1 to 10, you just have to multiply with the square root of 10. Okay? I already told you how to do that. If you didn't do the homework right, you have a chance to fix it. In fact, this is not so complicated. You don't need to really generate it. You don't really need to generate that random number 10,000 times and calculate the variance and mean. You don't need that, because I specifically requested the mean should be 20 and the variance should be 10, right? So you just need to shift and multiply. You don't need to make a lot. So this should be 1, but variance ideally it should be 1, so you don't have to calculate from that. It's very close to 1, but in fact this I even better solution. This should be 1. You understand? Yeah, and that mean should be, and the original mean should be 0, right? It's very close to 0, but it should be exactly 0. So you don't need to do that first step. It's okay? So you guys understand how to do the homework 1, right? So try to. What I really want is to ask you to figure out how to scale the variance and shift mean for Gaussian distribution. Okay, that's part of trick of 1A. Right, and then for 1B, for 1B, it's just do the counting. Okay, just do the counting. You throw the dice 40 times. Throw the coin 40 times, and you collect the positive. How many times positive, and then repeat 10,000 experiments. Okay, and then this is very good. Yeah, just basically just do the counting. Okay, just do the counting. And two students do different ways. So this one use the uniform because uniform distribution is between 0 and 1, right? So the cutoff number is 0.5. Okay, it's 0.5. So this is easy. Of course, you can use the Gaussian, and if there's a unit Gaussian, the cutoff number is 0. So that would work as well. Okay, so the second presentation use the Gaussian and then use the 0 as a cutoff. But that will be fine. That will be almost the same result in terms of generating the number of positive among 40s, and then you do the 10,000 rounds. Okay. Yeah, and then if you if you compare the result, superficially it looks similar. Superficially the figure looks similar, but as Papilla said, this is continuous. Okay, for this distribution, Gaussian distribution is a continuous distribution, but binomial distribution is discrete. Okay, so counts are integers. Right, so usually when you need to understand that, and then if you generate a Gaussian distribution enough times, there's a potential although the chance is very low, there's a potential of some negative numbers, okay? Right, but for binomial, it's impossible, so it could be between 0 and 40, okay? That's another difference, okay? So discrete number and continuous, discrete variables and continuous variables. All right, and then also another thing about central limit series is that no matter what kind of underlying distribution, a lot of underlying distribution is binomial, but if we sample from IID enough time, your data, follow Gaussian distribution. Okay, so there's another things you should figure out. So that's the key message I want to explain. All right, so and then question 2, there are different ways you can figure out how to do that. So logically, so Papilla has a logic is that what she did is that she first generated one random numbers from between 1 and 18, okay, and make it integer, right? But this is there's a small mistake here because when you say there are 3 ways you can make a continuous variable into integers. One is the flow, okay? Flow is no matter what, is the it's 1.5, 1.7, 1. Whatever is 1, right? The flow, 地板, okay, flow. Another one is ceiling. No matter what is 1 point anything, it become 2, right? 1 point. And integer will be 45, right? 45, right? So and in fact you want the chance to choose any number between 1 and 18 will be the same. Okay? If you do this as an integer, there's a slightly lower probability to choose 18. Slightly lower probability to choose 18. Okay? So either you have to use ceiling or you have to use floor. If you use ceiling, then your random number boundary will be between 0 and 18. But if you use floor, your boundary would be 1 to 18. But you should use floor or you should use ceiling. You cannot use integer. If you use integer, there's slightly biased probability to end. Okay? It's slightly biased probability, so it's less likely to choose the boundary numbers. So it's not good to use integer. Although by chance, if you run enough time, that 1 and 18 will appear. However, the chance is lower, so it's not fair. It's not fair. Okay, so you have to keep in mind that you either use floor or use ceiling, so all the numbers has equal probability to choose. All right, so there's there's an important logic that you keep in mind. How to make a number become integer, ceiling or floor or integer, depending on your research question. In this case, it's better to use ceiling or floor. Okay, not very good to use integer. Okay, that's one thing. All right, there's a second comment I have is that in this case, there will be another loop because what she did is that she chose one number and then she compared a second number with the previous one. Okay, and then if it's the same as the previous one, she throw away and choose another one, and until she choose another different one. Okay, and how about the third one?
If you don't create third one, like
Then how can you decide choose the third one?
then I need to I need to change my code or something.
Yeah, you have to do that. Otherwise, you can only choose 2 numbers.
Yes.
My question is that the
This is
homework.
only you can choose 2 numbers.
Yeah, so does not complete my homework. My homework is that you have to choose 2 students randomly, but avoid choosing the same students, right? So the logic is that you have to you can choose stuff from the beginning, or you can another possibility that you can choose assuming 1 and 5 already chosen, and then your program would run and then avoid choosing 1 and 5. That right, and then choose randomly. Okay. So this does not complete the job. This can only choose 1, 2 students, right? If you have third one, you have to compare the A and B and decide C. And if you choose D, you have to compare A and B and C and decide D, right? Something like that. If your logic is that, so you have to write the program like that. Right? Otherwise, this does not solve the homework completely. It's okay. You can have the time to fix your question homework. Okay. Then if Papilla successfully did that, choose A, B, C, D, E, F, G, blah, 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 until 18 students, there will be a challenge is that every time you choose randomly between 1 and 18, right? And when that allow a student already chosen, say for example, only number 18 was not chosen in A, or maybe number 17 and 6, I shouldn't say only 1 student, because there's only 1 student and we don't have to choose. If we left 2 students, 3 students say, we want to choose among the 3 students, then every time you run a random number between 1 and 18, and the chance to repeat already chosen is very high. So your loop continuously run endless until very low probability to choose the one is remaining, not yet chosen. Understand my question? You understand? So it's not very good. Because initially you quickly make a decision, but the decision making process becomes longer. Right? Everybody follow my concern about that this way? Okay, so this is not a very efficient way for this random selection program. Because initially very easy, but till the end, you have to compare all the same. No. In the end, is very time consuming to choose the number because you have always to compare. Right? It's not very good strategy. Okay. So I didn't. This will work because nowadays computer is very fast. You can just let it run 2 minutes, 5 minutes. You eventually choose the one you want, but it takes time. You don't want to do that. Okay. So how to pronounce your name? Gilbert? How to pronounce your name? Agno. Yeah, Agno did slightly better. What he did is a lot of still can be improved, but it's slightly better. Basically, what he did is that he chose to use ceiling, right? So this is correct, right? So there's equal probability to choose ceiling, and then he choose 2 numbers, right? And then actually he decided if the 2 numbers are the same, then he have to do that again, right? But this is a kind of wasting time. Again, it's wasting time. Okay, but I'll let you think about it. Maybe someone will get a solution. Okay, that's this part. This part I leave it open. I talk about second part first. This is a good idea. So basically, what he did, is that he then remove whatever is already selected, and he removed that numbers. Okay, and then put the remaining numbers in that vector. Right, so that already selected cannot be selected. That already been chosen cannot be selected again.
But my question is, I also try to do that, but then I think we should choose random. So if I got some number like from the previous, then is it like it will be random or?
Yeah, that's a question. That's an important question. That's actually the question is relevant back to the first part. So the question is that what's the best way? What is the most efficient? I like to spend some time on this because it is programming logic. Okay, that's a good issue to discuss. What is the best way to select a random number? In fact, when I say select 2 students, indeed you don't have to select 2 students at once. A better strategy is to select 1 student at once, and then second student. and run it 2 times, and then you can choose 2 students. So every time you need to select one. That would be the best strategy. Otherwise, you have to worry about that 2 students are the same or not, right? But this is the same question about that, you're choosing, select a student with already, you cannot select student that already selected, right? So in fact, you just need to select one student at a time and then compare and decide you choose second one. So this is a trick of the question. So it's not logically, it's not good idea to select 2 students at once because there's a high chance, there's a certain chance that 2 students are going to be the same, and they have to compare within that loop, but you also have to compare outside the loop. That's too much work in terms of coding, right? You just need to select one student at a time and then second student, right? So in fact, all you read, the key point is that you need to select this one student at a time and then avoid selecting the student already be chosen. Okay, so that's the logic. Okay, so let's go back to that the very fundamental question: how do you choose randomly between 1 and 18? How do you choose randomly between 1 and 18? All right, the certain simple logic is like that. You generate a random number between 1 and 18, and then you just choose one. That's very intuitive. That's how everybody would likely do. But this is not the best logic to generate the random number, right? Because keep in mind, what we really want to do is we should be able to generate a random number from 1 to 18. Okay? The issue is that we are going to generate a random number from 1 and 18 and select randomly. Okay, so does anyone solve the first part of this question differently? Okay, wrong. Like, come out here, explain to your classmates how you do that. You know?
I mean, I understand.
You understand? I thought you did differently, but you also do this way.
Yeah.
Okay, anyone do this part differently? You didn't use this. You didn't use this way. Everybody use this way. It's good. Okay, that's okay. That's certainly good because that's how I told you last week, right? So you follow very closely to my instruction how to do that. Okay, then I'll explain the concept of indexing and then the random sequence. All right. So keep in mind, this is where everybody understands, right? Another way to think about that is that say suppose we have 10 students we have to choose. I'm just going to write one. Three, until 10. So that's a 10 number you can choose. Certainly you have ceiling and you pick one. Right? Another way to think about it is if I want to choose the student randomly at once, how will you do? You are going to randomly shuffle that sequence. Right? You're going to randomly shuffle that sequence. Okay? And then you choose the first one. Always choose the first one, but you make a that sequence random， 让这个序列随机重新排列，然后呢，永远都取第一个，那产生的也是1到10随便选生一个，对不对 ？Okay, so as I give you a hint previously, you are allowed to use some built-in functions like a sort or a rank. I repeat a few times, but nobody listen to me. But that's okay. That's okay. That's why we need to have a lecture. So suppose what is sorting? We sort the numbers from small to large, right? Ranking is also set from small to large, right? Suppose you generate uniform random number 10 uniform random number. Suppose you generated 10 uniform random number between 0 and 1. Okay, so this one may be 0.5, and then will be 0.1. I didn't write that. Should be very long, right? I only put the first, and the second one maybe 0.85 and so on and so on, right? So you generate a random number, uniform random number. This is going to generate the number randomly between 0 and 1, right? Okay? You see? And then that 10 number will not repeat, right? According to my explanation last week, that first 10 number cannot repeat. They only repeated many, like infinite time after you select. So if you choose a 10 or 20, you will not repeat. Okay? But there is always some number bigger than others. So if you decide a sequence, so maybe this is rank 1, this is rank 2, maybe this is rank 3, maybe this is rank 4. So I give a rank until 10. Maybe, could be 10, could be here, right? Something like that. Okay? Is it okay? So when you generate that, you already generate a random rank or random sorting or whatever. You generate random rank. Right? If you convert the 10 random uniform numbers into their rank, so that 10 number, the location of that 10 number is in random sequence. Okay? Already in random sequence, and will not repeat. Impossible to repeat. You just need to choose first one. Right? Okay? Understand? Yes or no? Yes? Okay? So what you really should do is that so there's a concept of a number inside the, so in R, in R we have a vector or matrix, whatever you think about it, you store something, right? You store numbers inside. So this inside that is a number. 里面是数字，对不对？ Inside number. Now remember, I already convert that uniform random number into rank. So this is rank. Or you can use sorting, whatever. So that's the random number chosen. This is the vector represent the random number I choose between 0 and 1, right? Then I convert it into rank. Okay? And in that vector, that number represents a rank, and that rank actually is random sequence. Is okay? So this is the vector I stored. Okay? And we also understand inside that vector, so this is the index. This is index 1, this one is index 2, and so on and so forth until index 10, right? Right, so suppose I call this vector x. We all know x1 is equal to 2, right? Everybody know this. You know how these are, right? If s3 is equal to x3 is equal to 1 according to this vector. Okay? Is okay? Everybody okay with that? So this is called indexing. Right? This is the way to call a number. To call a number is called indexing. Right? So how can you get random number? First random number, we just say, suppose this is x. And you say, okay, I'm going to choose x1. Right? Number is 2. Number 2 students going to make a first presentation. Right? if I choose, of course, the first one I can choose whatever, but I always choose first one to be principal. I can always choose the last one, that's the same. Okay, but I can always choose the first one. Okay? Everybody happy with that? So then I can choose, if I choose first two. If I choose three, okay, first three. Whatever you like. Okay? Alright? Okay, then you solve the first part of your homework. Right, you solve the first part of your homework. Alright, and then the second part of homework is that now I already choose some number. Maybe I already choose already choose this number. I already have that number, right? So I compare a vector, this vector's length is 10, right? If I already have someone, if the number 3 already chosen, this is already, you have vector code already, whatever already is selected, stored that already. Okay? And then you have a original. You have original. Original will be 1 to 10, right? And now 3, 2, 1 already selected. You can compare this vector with that vector, right? And then you know 3, 2, 1 already selected. You get rid of that. So that's the idea of R. Get rid of that. If you get rid of that, now the remaining vector will be 1, 2, sorry. By chance 3 to 1, right? So I say the remaining will be from 4 to 10, right? Remaining number allowed to choose only 4 to 10. So then what you do? You just need to generate a random sequencing for 7 numbers, right? Or because I totally 10 students, 3 students already chosen. A remaining number 4 to 10. Right, so what do you then do? You just need to generate a uniform random number, 7 uniform random numbers. Okay? And then reshuffle that location. Reshuffle that. Now, again, that 4 to 10, you can imagine in the terms of indexing, again, that's totally 7. So you just need to figure out indexing, random index from 1 to 7, right? That number does not need to be starting from 1 or whatever, right? Because you have a vector stored that remaining. Now what you need to do is just that sequence become random, 4 to 10, that sequence become random. But it's already done here. Okay? You just need to distinguish the index and the real number in that index, in that box. You don't really need to care about what's the number in that box. Because after random shuffle, you always choose the first index. Okay? So initially 10 number, we random shuffle and choose the first one. That's the first step. If we are in a later stage, we just need to make a comparison and remove those already chosen, right? And store in a vector. And then we random shuffle that position, the sequence of that vector. And then always choose the first one. So it's impossible to choose what already chosen. And the comparison only needs to be, every loop, the comparison only needs to be done once. So you never repeat it because you already removed. You can make a comparison once and remove it from original and the random shuffle remaining. And always choose the first one. It's super efficient. Is it okay? Okay. If some of you are still confused, you can discuss among students. I think the majority of students already figure out, or if you don't feel comfortable, you can ask me during the break, or you can ask other students. It's okay? If you already did homework in the loop away, I don't mind, okay, as long as you can do your homework. We'll give you full grade, but if you like, you can try. This is super efficient way, all right? So the idea, again, let me explain again. The idea is that you have a list of students you want to choose, and you have another list of students already chosen, and you want to compare, okay, and then you choose for the remaining. That's a better way. And there's no need, when the homework say choose two students, we did no need to choose two students at once, because that is create more computation time in your code. Just choose one student every time and repeat. You do it twice, then you choose. And when you choose someone, they put it in the store in that already chosen, right? And then you can just compare. So that's how exactly your homework should look like. Okay? It will be even better. You write it as a function. The function take a two argument. Take a two argument. One argument is the number of students, right? Another argument would be the input vector store the students number who already been chosen. Okay? And then if you let initial stage, that will be your empty matrix, right? Because initially nobody chosen the first time, that input will be just an empty matrix. You compare the empty, of course you didn't remove anything. So the best homework, I'm looking forward to see your homework. The best homework for this would be you have a function. You have two input arguments. The first input argument you have number of students, right? And second input argument would be that vector store the student number who already chosen. Right? And in fact, output every time you just need to select one. And if you select one, you store that number into that as an input argument and run it another time. And if you do this, you can run that. If you do this and you run that, if you have totally 18 students, if you run that code 18 times, then you will select number all the students. So there will be a loop 18 times, call that function 18 times. That will complete your homework. Okay, that will be the best homework. I'll see who can make that. I'm looking forward. Okay? Question for that homework 2? Slightly challenging. In fact, logically looks simple, but if you want to make your code super efficient, you need to think about different logic. Okay? So that's also part of the purpose for this lecture. In fact, this is what the building function sample is doing. Okay, if you call the building function, there's a building function called a sample that allow you to random sample some numbers. That's exactly how that sample building function is doing, like that. Okay? But you are going to write your own sample function as a part of your learning process for this class. Any question? Okay, if not, what time is it now? Okay, we'll just take a 10 minutes break. Okay, maybe 14. We'll come back at 10:30. Okay, come back at 10:30. All right. So that's the real lecture start. Today we'll talk about bootstrap and jackknife approach for random sampling and why we need that approach. A very nice paper already put on NTU course called by Eber and Gong. They usually look at the bootstrap jackknife cross-validation. This very old paper is written for non-specialists. Please read this paper, okay? The different approach allow you to have a different uses. So today we will talk about bootstrap and the jackknife. And next week we'll talk about confidence interval based on this approach. And then after that we'll talk about the validation test. In a much later stage, EG will talk about cross-validation. So throughout the semester we explain the detail of all different kind of approach and how that will be useful to help our statistics, such as estimate standard error, confidence interval, and hypothesis testing. Okay, so pro and cons of this is called computer-intensive statistics approach. Advantage is intuitive, mathematically simple, non-parametric. You don't need to require that data follow any distribution. Few assumptions, handle very complicated problems. Okay. And this advantage is computational intensive. This is a very old term because now computer is super fast, so it's not that computer intensive anymore. Although still, it requires some kind of computation, and it requires programming skills. Of course, nowadays a lot of built-in function they can just call. They will do the computer statistics for you. But the main purpose for this class is that you write your own function. Okay, learn how you write a function that will do the same thing, because in the future there may be certain complicated research question you need to write your own code, because the built-in function has some kind of restriction. If you understand that philosophy, you are able to write your own code to do the random sampling and the statistics. Slightly complicated to explain, but I will try to explain that. Is less accurate when parametric assumptions are made. This is no longer hold nowadays, because this is only true if you cannot generate a sufficient number of random sampling. If you generate according to the mathematical theory, we generate infinite number of random sampling, that would be the same. Okay, but of course we cannot generate infinite number of random sampling, right? So of course this is less accurate. But certainly, if you generate like 10,000 times, 100,000 times random sampling, the accuracy is almost approximated to the true result, even when the parametric assumptions are made. Okay, so there's a lot of advantage. I feel that disadvantage is no longer such a problem. The only issue is that do you know how to program it? Okay, it's the only limitation here for most of us. Okay, why bootstrap? So consider a random sample of size n from an unknown probability distribution in the real line. Okay, so we have random variable x, and we choose random samples, and the x following some kind of distribution. This does not have to be a Gaussian, right? Because now we don't have to assume that this is IID. Okay, this is IID, right? But this not has to be Gaussian. And then anyway, we observe something, we collect data, and the expectation will be mean, right? Arithmetic mean. So that's the expectation S bar. And then we are going to use the S bar to infer the population mu, right? Population mean written as mu, right? So we're going to use S bar to infer mu. But we all understand, because the number of data is limited, so there's a standard error of mean, right? Standard error of mean tell you the uncertainty you have when you use S bar to infer mu, right? And then if your data follow Gaussian distribution, and we know we can calculate standard error of mean following this formula, right? Everybody understand this? Okay, so this is a standard deviation divided by square root of n, right? So this is approximate. This should be written as standard error. I forgot to fix this. This formula should be standard error of S bar, and not approximate sigma, because sigma is a true population standard error, right? But we don't know, but we're going to use that formula to approximate this. And there are several limitations of this approach. Okay, first, this approach assumes the data follow Gaussian distribution, and we say if we have random sampling IID, no matter whatever that underlying distribution is, we do IID, the data follow Gaussian. We always say that, but it's not necessarily true because there are some data that does not follow. Not necessarily true because we don't necessarily IID. We don't necessarily sample IID. So that data does not necessarily follow Gaussian distribution. Okay, if your data does not follow Gaussian distribution, of course you cannot use this formula. Okay, that's limitation one. And limitation two is that here we are interested in standard error of mean, but this in no way this can be generalized to other estimators. For example, median. Right? If we're interested in median, then how can you calculate standard deviation, standard error of median? Right? There's no formula. Even your data follow Gaussian distribution, there's no mathematical formula. There's no analytical solution for standard error of median. So it's impossible to estimate the standard error of median. Even data follow Gaussian distribution. So you can imagine many other things that you are not able to estimate the standard error of some other estimated statistical estimators, right? Because there may not be an analytical formula for that. So the second limitation, right? So with that, the problem is then how can you solve that problem using bootstrap? Okay. Let me explain the motivation of bootstraps. Suppose you want to estimate the attribute theta, for example, mean. Okay. You take a sample and then you estimate theta head. Theta head. This is true. For example, this is true population mean, and this is the sample mean. You're going to use this to approximate, infer this. Okay. And if you taken a different sample, you would have estimated slightly different theta head, right? If you take it, so if you have a lot of money, you are going to measure the body height of female student in NTU. You go out, you take 100 sample, you get a S bar, right? If you have a lot of time, you can go out to the second round of the sampling, you get a second S bar, okay? If you are very rich, you have a lot of time, you can do that 1,000 times, you can get 1,000 S bar, right? Because every time you get 100 data, you calculate S bar, and second time you get 100 data, calculate S bar, you can repeat 1,000 times. You get 1,000 S bar. You realize the 1,000 S bars are not the same. They may be similar, but they are not the same, right? 每次都不一样嘛，对 ，S bar 每次都不一样。In fact, that's the uncertainty of S bar. But if you get a 10,000 S bar, you can calculate standard deviation of that 10,000 S bar. That will be what? That will be a standard error of S bar, right? Okay? That's by definition standard error of S bar. The standard deviation of your S bar is the standard error of your S bar. If you can get 10,000 S bar, you're done, right? But no one will do that, right? No one will do that. If your data follow Gaussian, then you say, okay, there's a formula you can calculate, but if your data does not follow Gaussian, how can you do it? You have to go out 10,000 times, right? To solve that problem, if your data does not follow Gaussian, then you have to go out 10,000 times to get a standard error of your S bar. It's impossible to do that, but you can resample from your data 10,000 times. So that's called a bootstrap. You do not go out really resample everybody. You collect the data 10,000 times. If you have 100 data points, you can do resample with replacement 100. If you resample with replacement 100 numbers and repeat 10,000 times. Okay? So you with replacement, which means that the same number can be, you choose a number, you put it back. The same number can be chosen repeatedly. Okay, so it's called replacement. Okay, I already said that, in fact, in a real world situation, we want to get some estimate, and then in fact, with only one data set, but we can resample from the data set, okay, with replacement. That's called a bootstrap sample. And if then you have a bootstrap, I call it, S hat 1 prime, S hat 2 prime, so on and so forth. You can do that 10,000 times. Then standard deviation of that is going to give you a standard error of that. Okay? So that's the idea. Right, so you cannot do this real world, so you simulate the process. Okay? And the bootstrap sample size equal to the original sample size. Right? So again, suppose we have a data follow some kind of distribution, right? We get your S bar, right? And that has a variance like that, and you can then repeat the from sampling from your data, and then you can again calculate the theta hat for different time. You can get a lot of samples, and then you can then calculate the standard deviation of your theta hat. Okay. Ideally, mathematically, this formula we have to make exactly to the sigma hat with the factor n divided by n minus 1, right? Because there's 1 degree of freedom. Have to, but this does not help because in this case we are resampling from our data, and we can arbitrarily decide how many times we're going to resample from our data. Okay, if we resample many times, this does not have any effect because you resample 10,000 times and then this just factor out. Okay, this does not have a important influence of that. And this is just shifting the location, but the variance is going to be like the same. So we don't have to do that. If you do that, it will be the same result. That's not matter. Okay, so the bootstrap standard error of any parameter, let's just say this is mean. Okay, for example, this is mean. The standard error of mean is that, so this one, the theta I is your bootstrap sample mean. Okay, you can do that many times, b times. Okay, b times. Okay, b times the bootstrap sample mean. Okay. And what is theta dot? Okay, theta dot hat is the average of all theta I hat. Okay. And then you have to decide how many times, right? So usually 1,000 times, 10,000 times, right? Larger is good, but the larger need more computation time, of course. Note, your original data belong to one of the bootstraps because we require your original data to be one of your theta I in order to calculate the confidence interval of your theta I. Alright, so by definition, in fact, in order to calculate the standard error of theta I, you do not require this. However, conventionally, you include one of your original data as your theta I. Alright? And then because later on, next week, we need that because we want to calculate confidence interval of that. So we need that. It's okay? So in fact, when I say you make a bootstrap 1,000 times, you actually bootstrap 999 times plus the original data. Make it 1,000 times. It's okay? Let me explain using the very simple example. So that's original data. Okay? And I rank them. You don't need to rank them, but I just want to illustrate. So I rank them from small to large. And so you randomly select with replacement from this vector, and I also rank them, right? So you can, the 1.76, 1.67 can be chosen one time because with replacement, right? The same number can be chosen more than one time. So with replacement, right? So this one, and then this one, and this one. So not every number would be chosen in that bootstrap samples. Okay? So some number can be chosen more than once, but some number may not be chosen. Okay? And so that's your first bootstrap sample, and then your second bootstrap sample, and third bootstrap sample, and so on and so forth. Is okay? Is okay? And then your homework, of course, you want to do that, right? You want to choose resample, right? It's actually very easy. You just need to use a uniform random sampler. You just need to generate a uniform random number, right? And that can replace, so you don't even care about the sequence because the same number can be chosen more than once. Right? It's very easy. You just need to generate a uniform random number between 0 and 1, and then right? You know how to do that. Okay, you can repeat. The same number can be repeated. You take a CD that you want, by chance that number repeat. Okay, you need to generate the number between 0 and 10. Sorry, 1 and 10, right? And then some number repeat. Okay, is that part? You figure out, okay, that's your homework, you figure out how to do that. And then you repeat. So now, in this example, I have to explain a little bit. So in fact, in this example, I'm going to calculate standard error over median. Okay? There's no formula, there's no mathematical formula that allow you to calculate standard error over median. But we can do that using bootstrap. For this example, you can see if I rank them, the median is 2.17, right? And if I bootstrap, by chance, the median is 2.17. By chance, 1.7. By chance, 1.94. Alright? So you can generate a different median by bootstrap samples. And then you calculate the standard deviation of that, all this bootstrap median, you then get that is 0.219. That is the standard error of your median. Now you're done. Okay? Otherwise, it's impossible to calculate standard error median, but with bootstrap, you are able to calculate standard error median. Is it quite okay? Okay? But there are certain cases that bootstrap does not work. There are certain cases bootstrap does not work. In this example, I estimating the median, maximum value. Maximum value. I want to calculate the standard error of maxima if I bootstrap. No matter you bootstrap, by chance, no matter you do, the majority of the maxima value always 3.41, 3.41, 3.41. And then you will say the standard error of your maxima value is very small. This is wrong. Okay? Because maxima value is in the boundary. And boundary is set by the limit of your data. Right? If you bootstrap, you cannot be on the boundary because you bootstrap from the data. So bootstrap does not work for a boundary value, maxima, minima. If you want to understand your confidence interval for your maxima or minima, then the bootstrap approach fails. Okay? Okay. Right, and throughout this semester, we are not going to explain how you generate confidence interval for maxima. Okay, follow whiteboard distribution or some other difficult things. Okay, but usually we don't. Yeah, it's not common to try to estimate the confidence interval of your boundary. Right, so I will not explain that. But just the key message here is that the bootstrap approach failed in some cases. Okay, and your minima also, you cannot use bootstrap to estimate confidence interval, the standard error of minima. All right. So how to improve the efficiency of your bootstrap to avoid heterogeneity? Okay. So in a very simple example, we random sample 10 numbers, and then of course we just calculate median of that. Send up the 10 number and then bootstrap and calculate median again. Very easy. Okay. However, there are some cases it's more complicated. So this is some kind of transect design. This is some kind of actual survey. That survey is designed for sighting whale. Okay, sighting whale. So the ship is going like that, and I'm going to see, oh, is it a whale or not? Because I want to calculate the population size of a whale. So I go through that ocean Maybe it's a China Sea, and I go translate like that, and I have to see, okay, how many times I see the whale, okay? And then I'm going to estimate the density of whale, and then confidence interval of whale, and so on, okay? Now, if I simple-minded the bootstrap, if I do the simple-minded, this is translate 1, 2, 3, 4, 5, up to 11. If I do the simple-minded bootstrap, I will end up with bootstrap symbol like that. Because, for example, translate 1 and then translate 2 twice, translate 4 and translate 5 twice, and so on and so forth. And this one, like that, right? All these are all possible. However, if you take this bootstrap sample, you are going to missing the whole region here. Right? So now this is biased estimate of your theta hit. If you do this, this may be okay, but this is certainly biased. You don't want that. But you cannot check every time it's biased or not, right? So a better way to do the bootstrap, consider the geographic heterogeneity is that I can arbitrarily cut my translate into small pieces, right? Because you can get citing data from here to here, from here to here, here, whatever, right? You can then cut into small pieces. And now I bootstrap the smaller pieces. So I generate the bootstrap sample like that. So this will not, it's a very rare case have this one. But usually this is more homogeneous coverage of the whole geographic area. But this is a better bootstrap. This is a simple-minded bootstrap. Okay? So if your data contains some structure, you want to bootstrap them. You keep in mind that structure should be retained. So you have a better representative resample. And then the estimate, theta, will be more reliable. And then therefore the standard error of your theta will be more reliable. If you do this, your standard error of your theta is going to be exaggerated. Okay, exaggerated. Overestimate, yeah.
But the better one might also have some
Yeah, but chance is low. Chance is low. But the chance is very high if you do this. There's still some possible that some region, completely missing, but there will be very low chance. Low chance is okay because you are going to bootstrap that 10,000 times. If it appear 1 or 2 times, it's totally fine, right? Okay? Because that's reality. Oops. Also, if your sample size is very small, this is ridiculous example. I have only 4 data points. Of course, with 4 data points, you are not possible to do bootstrap. It does not help because 4 data points is too small, right? And suppose you have 10 data points only, right? And then you bootstrap. If you do the simple-minded bootstrap, there's by chance certain number get chosen more times. Maybe x1 get chosen more times, and s4 gets fewer times, right? But because the number is very small, I like everybody to be chosen almost equal probability, almost or even perfect equal probability. A better way is that I generated 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 b times, make a really long vector. And I randomize the sequence. Now you already know how to do that. You randomize the sequence and then cut it back. Okay, and then sample. Right. In that case, every number has equal probability. Exactly equal. If you do a random bootstrap, it's approximately equal probability. But you can make it exactly equal. Alright? If every data point, if the data point is very few and every data point is important, you can design a way to have a bootstrap sample that every data point have exactly equal probability, but not approximately equal. Okay? Depending on your research question. This is an example for calculate correlation coefficient. This is an example from that paper I asked you to read. That is a relationship scalar plot between the high school GPA and the student SAT score. So in the United States, students enter college and then need to take SAT, some kind of entrance exam, similar like Taiwan, but usually you can find some kind of reasonable positive correlation between their school performance and their exam score。OK， 考试成绩跟就学成绩、在学成绩差不多，有正相关。OK，so you can calculate. You can then calculate the correlation coefficient of this one. OK. And then we can then in a classical way, how can you calculate the confidence interval of the correlation coefficient? Anyone knows how to calculate confidence interval? If the data follow Gaussian distribution, how to calculate the confidence interval or the correlation coefficient? Nobody knows. Okay, yeah.
The estimate plus minus 1.96 of standard error.
Is incorrect. That is a general formula for estimates such as S bar. But correlation coefficient does not follow Gaussian distribution. You have to use a Fisher's Z transform, hyperbolic tangent transform, and then calculate and make it follow Gaussian and calculate the confidence interval and inverse hyperbolic tangent transform back to get a confidence interval. All right? If you don't remember, check your undergraduate statistics textbook. Okay? As you can see, that correlation coefficient does not follow Gaussian. Okay? Even the data follow Gaussian distribution, the correlation coefficient does not follow Gaussian distribution. Okay? So in order to make this Gaussian, you have to call the Fisher's Z transform, the hyperbolic tangent transform, and then you can make it Gaussian and make it base. It's slightly complicated. All right? If you don't remember, check your undergraduate textbook. But anyway, today we are not going to rely on Fisher. We're going to generate our own correlation coefficient by bootstrap. Okay? If you generate correlation coefficient by bootstrap, you do that many times, you make histogram looks like this. Right? Slightly different from the real Gaussian distribution, but more or less approximate to be that the correlation coefficient distribution. Okay? Of course, there is no guarantee our data are Gaussian, right? So if I'm going to do that research, I'm going to just believe my bootstrap confidence interval or bootstrap standard error. Okay? Okay, then the question is that how would you do the bootstrap from that data set? So keep in mind that correlation coefficient or regression. Another way, one way is to make a correlation coefficient. Another way is to make a regression line, right? You understand regression? So regression is by pair, right? So in this, there's x and y. In this case, you have to bootstrap sample by with pair. You cannot bootstrap randomly here and bootstrap randomly here. You need to line up, right? Line up and bootstrap by pair because they always pair. S and Y, S1 pair with Y1, S2 pair with Y2. You have to bootstrap randomly sample with Gaussian by pair. Okay? Cannot do independent random sampling. Is okay? That's a typical mistake that some people made. Okay? Typical mistake. All right. You have to you must sample with pair. Okay? That's called a non-parametric bootstrap because we don't assume any distribution and we just bootstrap randomly from the data, whatever data we have in hand, like by random sampling from the data, repeatedly. That's called a non-parametric bootstrap. Okay. However, there are certain cases if you believe you know the shape of your distribution. For example, you know the shape of your distribution for normal, gamma, or whatever. In fact, you can use this distribution to estimate the parameter describe the distribution. And then when you bootstrap sample, you can draw randomly from this ideal distribution you already know or you believe to be true. Then you don't bootstrap from your data, you bootstrap from your certain distribution. And that distribution could could be advised from your data. Right? For example, you have a certain data, and then you believe it follows some kind of Gaussian distribution, but you can calculate the mean and the variance of that Gaussian distribution, right? And then you can do the parametric bootstrap from that Gaussian distribution, but not from the data. Okay? You know now you already know how to do that because homework 1B is that, right? You generate random number from your decided Gaussian distribution. Right? If you believe and you have strong evidence supporting your decision, this is very good. Because if you generate random values draw randomly from your distribution, there's an infinite possibility you will not repeat. Right? Because it is a random number, right? You generate from distribution, that random value will not repeat. Right? You will never repeat it in R. If you constantly change the seed, then you will never repeat. In contrast, if you random sampling from your data, there is a limited number of combinations. Even you have 100 data points, if you sample many times, there's still limited number of combinations. So if you have 100 number of data, that's okay because 100 is a big number. You rarely repeat it, so you have another combination. However, you have only 10 data points. You bootstrap 10,000 times. There's likely a lot of bootstrap is like the same. You lose the combination. And in fact, the real world data is discrete. There's a discrete set of your data, discrete set of random samples you can generate. However, if you do a parametric bootstrap, there's infinite potential set of data you can generate and never repeat, right? So this data generated from the parametric bootstrap will be looks smooth, right? But if you generate the bootstrap sample from your real world data, it's going to look discrete. In fact, we have an example here, right? It looks not smooth. It looks a little bit strange. That is because this kind of why this is going down. This is because you have a limited possibility of generating your sample with your empirical data. So this does not look smooth. It's not too bad in general, right? But it's not smooth. Okay? But certainly if your sample size is very limited, this can be a problem. This can be a problem. Because it's not smooth, it looks very strange shape. Okay? So there are certain conditions. If you know the shape of distribution and really like to use that, take advantage of that, you can use parametric bootstrap. Okay? So let me give you an example. So that's a different season, say spring, summer, autumn, winter. That's some sort of arbitrary. It should be winter, the temperature is low. However, some data like different season, and then I get the data. So that's real world data. Okay. However, that real world data already missing. Given the data, someone already calculated the mean and the standard error and published in the paper. But real world data already missing. Okay? The question is that if you are going to ask whether the temperature increases through time. Alright? If you have a very simple-minded regression, you say, okay, that's 4 data points, I'm going to make a regression. Simple regression. I take this only 4 data points. I take a regression, okay? Right? But if you do this, you ignore the variability within that season, right? So you underestimate the uncertainty. Okay, and also you have a 4 data point. How can you make a regression? Right? Regression, we basically say, we need something like 30 data points in order to make a regression, right? And you say, okay, Zach, I already done bootstrap. I'm going to bootstrap regression, make it more reliable, but they have only 4 data points. Okay, you have only 4 data points. How can you make a bootstrap? The bootstrap sample is going to repeat again. It's not reliable at all. Okay, in this case, the parametric bootstrap could be a good idea. So you add a normal distributed random error term to each season mean based on its standard error and estimate regression coefficient and repeat many times. Say, now I have 4 data points. How can I generate a bootstrap? First, I choose the mean. Okay? And I choose a random number. The random number has a mean equal to 0, and then the variance calculated from that standard error, right? You use standard error, and you know the sample size, you know the variance, right? So suppose we know we have that data. So you this and add some kind of random deviation. So the data you choose maybe here, right? And this one and choose here, and you want to choose here. By chance, you could choose here. It's possible, right? Because of the Gaussian, there's a chance you can choose here and here. And then now you repeat it many times. Repeat many times. Then you can estimate the standard error of your regression coefficient. Otherwise, the standard error of your regression coefficient is going to be only rely on these 4 points. But it's not realistic because we know the data like that, but we already don't have that data. If we have that data, of course, we can just, bootstrap it. Right? There's so many data, we can just use the, simple non-parametric bootstrap because there are so many data, right? To make a regression. But now we don't have, we have only 4 data points and the data error. And then you believe the temperature can follow Gaussian distribution is a very easy assumption, understandable. Now you take advantage of parametric bootstrap. Then your confidence interval of your slope is going to be more reliable. It's okay? So there are certain cases you like to use parametric bootstrap, given some information and some belief or some knowledge. Okay. And the advantage of this is that you're going to generate your regression slope smoothly. You generate a 100 or 1000 slope, and that distribution of that slope is going to be very smooth because you rely on that Gaussian random numbers. Okay, it's going to be very smooth. All right, you can make something called a mixture bootstrap, something called normal smooth bootstrap. Right, you can bootstrap from that. In fact, more or less like that. More or less like that. But I bootstrap from real world samples. Then I randomly add some noise following that Gaussian distribution. But I purposely make the weighting smaller. Make the weighting smaller. This is called mixture bootstrap. This is not. This is some way to have in between, right? Pure parametric bootstrap and pure empirical non-parametric bootstrap. They can mix them in between. The advantage of mix them is that this one is going to have only discrete sample, limited number of possibility, and purely parametric is that you have to assume the purely Gaussian. But the mixture take advantage of both. By doing that, you can rely on if you make this very small, some small number, only 1/4, then you create discrete bootstrap values, but smooth it, so make it distributed much more smooth. Right? So that at a certain point, this is get a smooth sample. But then the difficulty is that how to decide? Is it 0.5, 0.25, it becomes a research question. How would you know? Right? Then that becomes slightly arbitrary. How to smooth it. So this is no longer not so popular, because it's hard difficult to decide this. Right? But there's a possibility to make that empirical bootstraps non-parametric smooth. Okay. In this paper, they try different approach. There is a bootstrap number 128 times, 500 times with some kind of smooth. Okay, and jackknife another approach. I will not. I'm going to explain later. I'm going to take a jackknife. And data method I already explained that using that assume that use the Taylor extension approach. Okay, called data method. And then normal theory that assume the data follow Gaussian distribution and you can calculate the standard error, right? You can have to visual Z transform and so on and so forth. So that's following normal theory. Okay. Then they compare different results. Right? Okay. What time is it? Okay. The amount of time. Bootstrap also allow you to estimate the bias of your sample, and then you may use that to do the bias correction. The bootstrap sampling, and then you can calculate the bootstrap distribution and estimate the bootstrap parameters, right? And then if the subsampling method or analysis introduce a bias, then you can then calculate the bias correction that you corrected this. Let me say let me make an example. You want to know the mean size of fish caught at sea, okay? And the landing include 1,200 fish measured at dock. Some fish people do the juggling and then catch 200 fish and measure their size. Okay. However, there's a regulation. Fishermen are only allowed to keep 2 undersized fish a day. As such, the data you get from the size distribution of landing is biased of the fish, right? Because it does not represent the fish caught, because there are some fish slow back, it didn't measure, right? Because your fish is smaller than 28 inch, you have to slow back. So that's the data you can, this is the data. This may be the true data. This may be the true data. Okay? But the number and the probability here are underestimated because you can keep only two. If the third one you will slow back. So this underestimated probability here is underestimated here. If you take the mean of all this data is overestimated, right? It's okay? Because I slow back a lot of species is smaller than 28 inch. Right? But your idea is that you want to know the real mean of all the fish supposedly caught. Right? But now with this data you underestimate. Okay? But you don't know how much you underestimate. You don't know how much you underestimate. But one possible way, maybe not best way, but one possible way to resolve that bias. So because of this you have a bias, right? So you have to figure out how much the bias is introduced. Okay? You can do some simulation. Now, you draw a number of fish landed. So that's your data. This data is not a very good data set because this data have underestimated here probability and therefore overestimated the mean size, right? But now I'm going to draw randomly, so this is already IID because that distribution already decided. I'm doing IID and generate the distribution. Okay, generate some kind of distribution. Now I'm going to the second step. I'm going to do fishing from this data set. And when I do the fishing, I saw fish back if there are more than 2 are smaller than 20 inch. Okay, so the simulator, the fishing, the jiggler is doing. Okay, and by doing so, you can then figure out your bias. Okay, that's one possible way. This is certainly may not be the best way, but it's a possible way to estimate the bias of your mean. Okay, because the jiggler is so bad some fish. Okay. All right. I'm going before I. All right. I need to talk about jackknife. Maybe I come back later on this, right? Because I have to talk jackknife, but then I come back to regression. Okay, so far okay with bootstrap. So far okay with bootstrap. I'm going to talk about jackknife. Okay. So what is a jackknife? So again, we are going to estimate something, and that's your data, and then you're going to use the theta head to estimate your theta, right? The same question. This is a very old method. This is invented in the 1950s. Say, okay, now I'm going to estimate something. Now I'm going to delete one data. Delete only one data. So this is called as theta head minus j. So it means that j's data is already deleted. So in this case, I totally have a sample size n. The jackknife sample has a sample size n minus 1. N minus 1. Right? And you can sequentially first jackknife sample remove the first sample, another jackknife remove second sample, and so on and so forth. So there are totally n possible jackknife, right? N possible jackknife. Only n possible. Already fixed. Only n possible jackknife. Okay, I call it every time each one I call it theta head minus j. Alright? And then with this n possible version of theta head, I can calculate again theta dot. That's the average of all your jackknife estimates. Right? Okay? And then the variance of your theta head following this formula. Right? Why is n minus 1? Because totally every time I remove the 1 numbers, and I need to put it back. The variance is reduced because fewer numbers or fewer variance, right? So I need to put it back. Okay, and then standard error over your theta head following is the standard deviation of this form. So it's okay. So you can use jackknife to estimate the standard error over your whatever statistics following this formula. Almost the same as concept of jackknife. Very similar to the concept as bootstrap. But in this case, I sample, remove only one. Okay, remove only one. And there are only n possibilities. So it's very simple. Okay, and with that, you can calculate your standard error. And it was introduced a long time ago. Okay, and this is a linear approximation to the bootstrap, but not good as bootstrap because there are limited number of possibilities. But bootstrap a lot of possibilities because you can sample with replacement. But jackknife only limited number of possibilities, only n possibilities to generate your sample. Okay, so this is a jackknife estimation of your mean. So that's original data. So the first one, jackknife one, only 10, right? So only 10 possibility, right? So you remove first one, second one, and so on and so forth, right? And so that's the original mean, and that's jackknife mean. So jackknife mean 1, jackknife mean 2, jackknife mean 3, jackknife mean 4, mean so on and so forth, right? You only totally 10 possibility. Okay, and then you can calculate standard error of mean. If you assume that the data follow Gaussian distribution, you can get analytical standard error of mean, right? You remember the formula, and that's the jackknife mean, and the standard error of jackknife mean is exactly the same. It's actually exactly the same. It's actually exactly the same because of this formula, you can do the math. It's exactly the same. Because every time you remove one number, so all the possible combinations is exactly the same. So after you do all the math, you following all this computational procedure, the standard error of mean is exactly the standard error of mean calculated from an analytical solution, which is the standard deviation divided square root n. Is exactly the same. Okay, so computationally, you do not assume any formula, computationally, you do not need to assume any formula. You can jackknife, you can calculate standard error or mean using jackknife. But in fact, that computational result is exactly the same as this result because of mathematical identity. It's exactly the same. Okay, if you don't believe it, go ahead and try with part of your homework, and then you can figure out the mathematical formula. Okay? But certainly this can allow you to estimate the median, right? Right? Because we don't have an analytical solution for the standard error or median, I'm going to use the jackknife. But if you use jackknife, all the median is exactly the same. The standard error is 0. So jackknife is not good at estimate standard error of median because of limitation. Because every time we remove one number, and this number does not affect median in any case. Right, but we know from bootstrap the standard error or median is this number. But if you use jackknife, it does not work. Or it does not work. Okay, so that is why the concept of jackknife was proposed in 1958. It's never popular as a way to estimate the standard error of something or the estimate because of some kind of mathematical limitation here. Okay, but they are certainly usefulness of this approach in some statistical questions. Yeah, but generally, jackknife is not so reliable or not so efficient compared to bootstrap. Okay, but computationally very easy. Computationally very easy. You can try, if you like, as an exercise, compare the bootstrap and jackknife using the model data. Because it is model data, you know the true answer, right? You can then figure out the reliability of your program, your computer program. Okay. So suppose I generate a normal distribution. Suppose a vector A generated data set A generated from this, and data set B generated from this, and calculate the ratio. Okay? And because I can generate infinite numbers, so I really know the true answer. Almost true answer I know because I can generate it many, many times. Right? But suppose C is sampled 10 times, and we want to estimate the standard error of the mean and median of such a sample taken from this distribution. Okay, and then you taking multiple times or 10 data sets from this distribution, we can calculate the true standard error of the mean, the median. Okay, so you can then can do this a lot of time, you can get the true because this can be repeatedly do, so you know the true answer. Right? And then assume if we have take only one sample, we have only 10 data points. We need to like to use that 10 data point to estimate the standard error. We can use an analytical solution. We can use a jackknife. We can use a bootstrap. Okay. And then the mean. That's a sample. Okay. And then we can calculate the mean and calculate the standard error of mean. Those is all from analytical solution. And the standard or median cannot be calculated because no analytical solution for standard error or median. Okay. And then if we jackknife, then we can calculate jackknife mean, jackknife median, and that's all the jackknife samples. Only 10 possibility, but only 10 possibility. So you can calculate jackknife standard error, jackknife mean, standard error from jackknife median is too small. Okay, and then you can do the same thing, but from bootstrap sample. Many bootstrap sample I can do. Then I can calculate bootstrap mean, bootstrap median, and standard error mean, standard error. Okay, and then you will realize that the standard error, bootstrap standard error mean, and bootstrap standard error median is going to be more reliable. Okay, compared to this result. Of course, you cannot do this, but compared to this result, you can find that the bootstrap approach reasonably good, because you know the true answer. You know the true answer. We can compare it. Okay. So be careful with the method you choose. Okay, be careful with the method you choose. Alright, and then I say, well, then jackknife is not so useful as an approach to estimate standard error or something. Then why do we need to learn jackknife? Jackknife is useful to estimate the bias for bias correction. This is in fact introduced a long time ago by this mathematician. The bias is n minus 1 multiplied with this. And this one is the Euler average from your jackknife. Right? And this is the sample estimate. Okay, this is jackknife mean. Okay, and this is the sample mean, and that is the bias. Okay, so the corrected estimate looks like this. Let me explain a little bit on the jackknife bias correction. Estimation of some kind of theta, we can assume they follow some kind of Taylor expansion, some type of Taylor expansion. Okay, because they have sample size n, so the Taylor expansion looks like this. Okay. If you do the jackknife estimates, then because jackknife has sample size n minus 1, right? So the approximation follow Taylor expansion looks like this. And if we try to solve with these two formula, you multiply first equation by n and second equation by n minus 1 and so on, you can get that. In subtract, you get this. And because this becomes alternate term, the jackknife bias correction, I just copied it from previous page. And this is the less biased estimator because A1 term has been eliminated and A2 has higher term, have an alternating sign. And therefore, you have the bias corrected estimator following this formula, which is the same, which is this formula. Okay? There's somehow is usefulness of the jackknife to do the bias correction. All right, that's a final topic is ongoing research called the subsampling. So I have jackknife, I sampled n minus 1 from the data, right? If I use the bootstrap, I repeat the sampling with the replacement. Now we complain the jackknife is not so useful because there's only n minus 1 possibility, right? And then the resampling is not efficient. All right. However, the professor of politics is a mathematician in UCSD. He's an economist. He proposed an idea, is an extension of jackknife idea. He called it subsampling. He said, I'm going to sample n minus d data. Sample n minus d data, not n minus 1, n minus d data. If I do this, the maximum number of subsampling becomes substantially increased. You have a lot of times you can choose. If you only jackknife, there's only n possibilities. But if you n minus d, the possibility become much larger. And therefore, if you have a larger number of resampling, then you can do a lot of things. Okay? So, this is okay. Yeah, I don't expect you understand all these details. I'll just give you some ideas. This is an ongoing research topic. What is the bias of theta and what is the variance of your theta, and how can you do that using the subsampling? Okay, the subsampling you can make the subsampling efficient enough that it has good estimate of standard error of your estimator. Okay, we solve the issue of jackmap. Okay, but then the question is then how do you determine these parameters? How do you determine these parameters? This becomes a tricky question depending on a lot on the distribution of your sample, the length of your sample become more complicated. Right? And therefore, the purely subsampling approach is not mathematically reasonable, but not so popular to use the subsampling approach to estimate a standard error of something. Okay, because a lot of mathematical detail remain to be worked out. Right? But subsampling is very useful for some other purpose that we'll talk about next week. So procedure is not so difficult because procedure is that you suppose you can just choose, you just randomly remove certain numbers and then keep the remaining, and then you randomly choose these subsamples. Okay. And subsample is useful for the weakly dependent data. Weakly dependent data. For example, your data are collected on the distribution of animal along the transects, or then the data is not independent because it's along the transect. So that data are very close to this site. I collect data here, collect data here. The neighborhoods are very close. So it's not independent. Okay, so we cannot do the very simple-minded bootstrap, right? Because this is very similar to this one, so they cannot be chosen random. All right, you need to consider some kind of correlation among the sites. Okay. So if you generate, so you calculate some kind of estimate, and if you do the bootstraps to calculate the standard error, the standard error is going to be underestimated because the data should not be independent, but bootstrap assuming data are independent. Okay. The one possibility is that you have to choose the sample in the reasonable area, right? If you understand the correlation, first sample I choose this area, the content variance sample, and then I come here and choose the area and this sample, right? So you kind of doing the concept subsampling, okay? And then all these sample has a weakly dependent data, exactly the same as the original data, okay? And if you do the bootstrap that way, it's called a weakly dependent bootstrap approach. Then you can generate a confidence interval or standard error of your estimate more reliably, really incorporate that structure of the data, the dependence of data. Okay, so even subsampling approach is difficult to implement because it's complicated to decide the different delta and all the parameters. More parameters you have to estimate. But the concept would be useful to solve the problem of weakly dependent data. Okay? And then next week I will explain more detail when we estimate the confidence interval, how can we solve the issue of weakly dependent data using something called a weakly dependent bootstrap. Okay, and the concept borrowed from subsampling idea. Okay. Before I talk about homework, I'd like to come back a little bit on the regression question, because I like you to improve your computation efficiency. Okay, the homework involves regression, X and Y. Okay, and then everybody know how to calculate regression. If you use R, it's called LM model, right? You call it a model, and they get an estimate. You get the estimate of your regression coefficient. You get alpha, you get a beta 1, right? But in fact, if you call the LM model, it did a lot of calculation. Not only the alpha and beta, it tell you a lot of confidence interval, give you a lot of output. But you don't want that. If you just want to get the confidence interval of your beta 1, you don't want to call LM. It's wasting time. Although your computation is computer is very fast, it doesn't matter. But in reality, if you have really big data set, you really need to repeat a lot of computation. It's not good idea. You call LLM function repeatedly. Okay. So if you are interested only in alpha and beta, if you are interested in only in alpha and beta and bootstrap alpha and beta, you don't need to call LLM. You just need to figure out how to solve alpha and beta algebraically. Okay, the linear algebra. So I have a vector y is your dependent variable. I have many x. I have x1, x2, x1, and so on. And I have a repeat measurement. I have different measurement, but then the sampling. So I have matrix like that. Right, so this is multivariate regression question. 多变数回归, yeah, the multivariate regression question, right? And always we need to first add the first column as 1, right? Because this column, the coefficient for this column is the intercept. Is it okay? And the coefficient for coefficient b, so that's the intercept. That's the regression coefficient 1, regression coefficient 2, and so on and so forth for each variable. You want to get that, right? You really want to get that. And you bootstrap and repeat it. You generate bootstrap sample here, and you get the bootstrap b, right? You repeat it 10,000 times. Okay? That's what you want to do for your homework. And then we have a column of error, right? You have y and y hat, right? Y hat is the regression predicted. 预测值嘛，对不对 ？predicted, and the error is the difference between y and y hat. Right? So that's what you learn from your undergraduate regression. Again, kids, if you don't remember your undergraduate regression, take your undergraduate statistics textbook. Explain. Okay, in your undergraduate statistics textbook. So here is a dimension n1, and this one is dimension n and k plus 1. K is the number of x variables, n is your sample size, right? And b is the vector k plus 1. K indicated for regression for each variables, and this one is for intercept. Right? And then you have a dimension n is your error because they are totally n sample size. We are clear with that, right? Okay? With that setting, we have this data. We have this data. You just need to put it in a reasonable way. Don't forget this one. You have this data and this data. That's your data you collected. Our objective is calculate B. First, certainly we're also interested in E, but now just focus on B because we want to get B and bootstrap B and come to the interval of B. Okay? So what is B? The linear algebra solution of B is this. Why? Let's make it here. So this is this one, right? So this one. So any y, you have a matrix X. If you find your best fit, linear least square solution of B, right? And then the remaining is the residual. It's called E. It's called residual, right? So I want to find B. So that is the least square best fit, least square solution. So I'll look at the least square solution. We want to get B, so I'm going to do some algebra. I multiply both sides S prime. S prime is S transpose. S transpose. Okay, S transpose. Okay? And then if I do this, I end up with this. Because S prime multiplied with E is 0 by definition is 0 because error should supposedly be independent of your X matrix. That by definition is the solution for this square solution. Okay, this square solution by definition this is independent. Okay, so this is 0. And then now to get B, you need to remove this to this side, so you need to calculate the inverse. Okay, this should take it from this side. So it's the inverse in linear algebra. So you take the inverse, okay, multiply with this inverse. And by definition, this is just B. This is B. Okay, by definition, this is right hand side is B. And that's what you need to do. Okay? That is why B is this solution. That is why this is how you calculate B. Okay? So in R, how can you calculate this formula? You have this, you have this. right? You can transpose, right? In R, you can transpose 转至 X matrix, right? And this can be calculated and get the inverse. I get the inverse. In R, how can you get the inverse? Using solve function. Okay, you can Google how to use the solve function to calculate the inverse of this. So this is transpose and multiply and take the inverse. Okay, multiply with S prime and multiply with B. Why you get B? You can write a single one line of code. And there's a built-in linear algebra function. You can do this super fast. Okay? So R has an engine to do the linear algebra super fast. Okay? This is involved in linear algebra. I'm not going to explain. The single value solution, single value decomposition, and take the inverse and very fast. It's written in C engine. Okay, calculate outside and take it back. Okay, so if you do the linear algebra, it's going to be very fast. Then in MATLAB, if you use MATLAB, even faster, you can x backslash y as 反除 y. Okay, back. You write this s backslash y, get b. If you use MATLAB. Again, there's a built-in engine, linear algebra engine of MATLAB. Because again, the reason I emphasize a lot of time to use your matrix operation for your coding. Okay, try to use linear algebra for your coding because MATLAB they have a built-in linear algebra engine. Do that linear algebra computation super fast. Okay, instead of loop. Okay, and then if you write a code like that, so you just need to get inverse s prime x multiply with s prime multiply with y, you get b. So it's one line of code get b. Right? Without calling the LN function and then try to get the element from LN function and like that. Okay, it's okay. So that's if you want to call LN function, that's fine. I don't mind. All right, but just a trick, just from a mathematical point of view, this is very fast, and then you can solve your linear regression repeatedly, very, very fast. Okay. That's okay. This is for MATLAB. You can do that for R. All right, and then come to the end of the lecture. Let me explain the homework. So you have a data set called fish and copper density. I put the mock data on that, and maybe in the first week of EJ also put some data sets. Right, that's exactly the same data. Okay, in that data set contains environmental variables and fish density, copper density, and so on. If you open up the mock data, okay? So there's a column called fish data, there's a column called copper density data, okay? Of course, there are seasons and space and so on. Now, I don't mind. Now I assume all the data points are sampled independently. Okay, you don't worry about spatial variation. You don't worry about the season. Okay, assuming all the data are sampled independently. Okay, all the data get independently. Okay, and then I want you to calculate the mean and standard error of mean for fish and the copper density independently. Okay, independently. The total density, total fish density, total copper density. Okay, there are only, I think, 36 data points. Okay, so you use that 36 data point that you calculate mean and calculate standard error of mean, right? You can use the first. You want to use the normal theory. Normal theory very easy, right? Standard deviation divided square root of n, right? Okay, so you assuming data follow Gaussian distribution and they use analytical solution. So this everybody knows how to do that. Okay, but you don't need to derive the mathematical formula or things like that. You can just do that. Okay, very easy. And then the challenging part is you want to generate a bootstrap sample and use bootstrap approach to calculate the bootstrap mean b times, okay, 1,000 times, and then you use the formula to calculate standard error, bootstrap standard error of mean, okay? And then you can generate 1,000 times, right? So you can make a histogram of your 1,000 times bootstrap mean. Okay, make it strong. You looks like almost Gaussian. looks like almost Gaussian. Yeah, but you have to try that. Okay. And then second question is you calculate the median. There's built-in function median, right? From that R you can use. And then you bootstrap the standard error of median. Of course, that would be repeat this part of standard and non-parametric to bootstrap, and then you calculate standard error median for fish and the cohort density independently. Again, you plot the histogram. Okay. And third question is the regression. Now, because the fish and cohort data are impaired, now I'm asking the relationship between fish density and cohort density. So this is a dependent variable, this is y, this is x. So you make a regression, Again, you can do the Collier LM model, or you can do the linear algebra. Anyway, you can get the beta 0, beta 1, right? And then you repeat it using the non-parametric bootstrap. 1,000 times, then you get the histogram of beta 0 and beta 1. Okay, and with that, you can calculate the standard error of beta 0 and beta 1. Is it okay? Any question on homework? And you are not to allow built-in bootstrap or sampling function in our method. Okay, I repeated it. Don't use, because the homework here is actually write your own sampling function to do the bootstrap. Okay, no built-in function allowed. Okay, or you can use median, mean, median, variance, sum, etc. So these are allowed. Okay, yeah, but not built-in function not allowed. Okay. You should, the hint is you can use the uniform random number generator, uniform random number to generate the bootstrap samples. Okay, that's one hint. The second hint is that when doing a regression, sample is paired. Okay? My explanation clear enough for your homework? Okay? That's all. And let's continue. Basically, repeat the homework using jackknife. The same homework, but instead of a bootstrap, using jackknife. Alright? And then finally, you compare the homework from jackknife and bootstrap. And also, normal theory. Of course, you cannot get the data, you cannot get the standard error of the median from normal theory. That's okay. You just say it's not possible to get. Yeah, but for standard error of mean, you should be able to get from normal theory. So you have a parametric approach, you have a bootstrap approach, you have a jackknife approach, okay? And you want to make a comparison, right? So ideally, you figure out this is more efficient, and this is sometimes work, sometimes not work. Sometimes this is exactly the same that because we already explained it in the lecture. Okay, again, write your uncle. Question for homework? If not, volunteer for homework presentation for next week. Nobody done? Yes, very good. Another one. This is easier than you think because the later one. Okay, good. Write your name here. This is easy. Actually, this is actually not so difficult. This is easy that it looks. Okay, but the future one is more difficult. that computation homework is only possible to get it more and more difficult. The most difficult one is the final homework, neural network. Okay, neural network bit propagation, that would be the most difficult one. But all right, it's good. We have two. All right, see you next week.